Looking at number 7 on review for exam 2, number A, version A, we're told in a game you have a 1/48th probability of winning $143 and a 47/48th probability of losing 10. What's your expected winning? All right, and we really want to read that as saying what's your expected value for this problem. When we're doing expected value problems, we're going to want to look at a probability distribution table, which we're going to list some number or value and their associated probability. Frequently, it's nice to kind of look at what can happen. So in this problem, we can win or lose. There's really only two distinct things that can happen. If you win $143. You have a 1/48th probability, or whatever that works out to as a decimal, probability of winning. And if you lose 10. We're going to write that as a -10 with the 47/48 probability of that happening. The expected value is the product of 143 times 148 plus the product -10 times 47/48. That's really looking like a minus to me, but same thing. And when I work this out, I should get a -6.8125 or so, or -$6.81. And the concept here is, if you repeatedly played this game over and over, we'd expect on average to lose about $6.81 per time played. That would be the average amount we'd expect to lose. The problems 7 through 10 on review for exam 2 version A are that type of problem, and let's look at a couple more. In 8, we're told Bob and Fred play the following game. Bob rolls a single die. If an even number results, Bob must pay Fred the number of dollars indicated on the number rolled. On the other hand, if an odd number is rolled, Fred must pay Bob the number of dollars indicated. Find Bob's expectation. And I'm going to point out here, one thing I'm going to stress here is Bob's expectation. So this is dealing with Bob. This is all about Bob. All right, any baby steps we need, we'll deal with Bob. All right, so looking at this. Numbers, associated probabilities. Okay, so reading through this, if an even number results, Bob must pay Fred the number of dollars indicated. In this example, there's 3 different even numbers that can happen. You get a 2, so he's going to pay Fred 2. That's a -2 to Bob, -4 to Bob if his 4 comes up, and -6 to Bob if Bob comes up. So this is kind of the even numbers / loss scenario. You don't need to write that down, or a losing scenario, but that's kind of what's going on in the problem. It can be useful to think about that. If an odd comes up, or he wins, that's the same thing. It's a 1, 3, or 5. Right, each of these is equally likely. They're all 1/6 probability of happening. So the expected value would be a -2 times 1/6 plus a -4 times 1/6 plus a -6 times 1/6 plus 1 times 1/6 plus 3 times 1/6 plus 5 times 1/6. Hopefully you notice those are all being multiplied times 1/6. So it's 1/6 times -2 plus a -4 plus a -6 plus 1 plus 3 plus 5. And this is going to work out to be, once I multiply this all out and things work out nicely, this should be -0.5, which looks like D. Number 9 reads, at age 50, Anne must choose between taking $19,000 at age 60 if she's alive then, or $32,000 at age 70 if she's alive then. The probability for a person aged 50 to be living at 60, according to this problem, is 0.81, and 0.55 to be alive at 70. Okay, you may recognize these numbers from our assignments that we've done. Those are horribly unrealistic. The probability of being alive at age 60 is much, much, much higher than that. It's the same at 70 if you're already 50, but regardless, we're going to use those numbers for these problems. We have two options here. We have the 60-year-old option, we have the 70-year-old option, and we're going to find the expected value of each of these. And we're going to notice one thing that's implicit in these two problems as we go through this. So at age, if she's going to take the payout at 60, she can get $19,000, and the probability of her living to do that is 0.81. On these expected values, we need to be listing out all of the possible things that can happen. And that would mean our probabilities need to add up to 1 here. So this probability here should be 0.19. And if she didn't live to age 60 from the problem, well, it looks like she's not making anything, or she's not earning anything. So we're going to put a 0 there. That seems to be what's going on. And we're going to end up, comparing expected values in these problems. So finding the expected value here, we're going to get 19,000 times 0.81 plus 0 times who cares what. It's still 0. but this should work out to be some value, and I'll plug this into the Excel off to the side here and see this is 19,000 times 0.81 with an equal sign in the front is about $15,390 or so. For number 70, same basic setup. The appropriate numbers are 32,000 with probability 0.55 or 0 with probability 0.45. I'm going to reiterate that 0.55 is way, way low. It should be like 0.85 or 0.9. Alright, 32,000 times 0.55 plus 0 times 0.45. Plugging that in to my calculator. It gives me 17,600. In the context of this problem, it looks like I want the one with the higher number here, so I'm going to want to take the payout for age 70. At this point, I'm going to stop and say this problem may seem very obtuse, or this may seem very strange. If you ever are given a pension at any company you're at, or make any decisions about life insurance, this is effectively what a lot of those decisions come down to, is having some relationship like this. You can get a smaller amount at an earlier age or a much, much larger amount at a later age, and you will be very likely to have to make a decision of this sort throughout your life. So this is probably one of the most realistic sort of problems we've looked at throughout the whole semester, even if it seems a little strange or possibly morbid. Number 10 reads, you're playing a game in which a single die is rolled. If a 2 or 5 comes up, you win $12, otherwise you lose 3. For this problem, same basic idea, number, probability. You can win, or you can lose. If you win $12. If you lose $3. The probability of winning is 2 ways out of 6. That's 2 out of 6. You can simplify that to 1/3 if you want. If not, you're going to get 4/6 over there. It doesn't really matter. So just going with this, we're going to get 12 times 2/6 plus a -3 times 4/6. I believe that works out to be 4 minus 2 is 2. So the expected value of the game is currently $2. For the game to be fair, we would need a long-term expected value of 0. The way to make that happen is to charge $2. So the current expected value of the game is what you would have to pay for the game to be considered fair. So that's how you do number 10.